Okay, so this is chapter 6, sampling, case selection as a basis for inference. Okay, so we're going to talk about everything related to sampling in this lecture, from the sampling process itself, the principles of probability sampling, and lastly, non-probability sampling. So the chapter starts with this diagram explaining the sampling process, or the initial steps of the sampling process. Like with everything we've talked about so far, the first step is developing or formulating a research question. So depending on what your question is asking, you're going to select a general research approach and determine a unit of analysis. So to give an example of this, if my research question was, what are the experiences of students in a research methodology, or a research methods sociology course, my approach could be a survey that offers open-ended options for response, and the unit of analysis would be the experiences of students. So the next step is to choose a general sampling strategy. So depending on your research, you're going to need to determine if you're going to use probability sampling or non-probability sampling. And we're going to get into how you can figure out which is best for which studies in a bit. But continuing with my example, sampling involves types of research and the scope of it, right? So I'll give you more examples as we go about how this works. So when it comes to sampling and inference, the whole point of probability is to make some sort of inference about the overall population that you're studying. So remember, your population is the overall group you're interested in studying, like in my example, students in a research methods sociology course. But your sample is a select part of that overall population that you're studying. Meaning, if I gave a survey to a random sample of students in this class, I could infer what other students in the course have experienced, or of students in other similar courses if I've done my sampling correctly. So the point is inference, to say that you found what you found in your surveys or interviews or whatever method you choose is the reflection of the responses of the overall population, not just of your sample. So this is why the appropriate sampling is super important. But before we get into how that works, I need to set up what probability sampling is and what non-probability sampling is in the rest of this lecture. So this figure on the right is saying that if you pick a small sample of a population, the goal is to infer the findings back to the overall population that you're studying. Okay, so when it comes to probability and random selection, what is probability? Probability is just the odds or chances that something will occur. So when we talk about probability in research methods, we aren't talking about your odds in Vegas as much as we're looking at the sampling process of respondents for your research. So probability sampling is based on random selection. This just means that each case has a known chance of being selected. So for example, every fourth person in the course would be selected, or the classic, put everyone's name in a hat and pull them out, where every person has the same chance of being selected. Also, the chances of selecting one case are independent of the chances of selecting another. So as you guys looked at in the weekly research assignment, the gender breakdown of the class is a little more female than male. So if I just divided the class by gender identity and then selected randomly from those categories, if they're not well balanced, that could affect the randomness of selection, right? And lastly, selection can't involve physical mixing and human judgment. So if for any reason the selection process favors certain cases, or if the selection of one case increases or decreases the likelihood that another will be selected, then the selection itself is biased. So in the book, they give the example that if you were going to study, well, they didn't give the example of Calci-Fullerton students, but let's just say Calci-Fullerton students, right? So if you're going to study Calci-Fullerton students and you decided to pick your friends as a sample, they may not be a representative sample of the overall Calci-Fullerton population. Unless you have that friend group that's like every 90s cartoon where they had that like faux diversity thing where there's token characters of different minority groups. But in reality, your friends are probably not that, fake thing from 90s cartoons. They're going to be a biased sample, right? Just as if I interviewed everyone in this class and tried to infer it to the overall Cal State Fullerton population, that would be biased as well. Because there may be something different about sociology students than others. Or there may be something different because you're taking a required class, right, than other students. So I could infer it to the population of sociology students taking research methods, but not to those taking other classes or those in other disciplines, let alone the entire generalized student population. So this is where sampling is important, but we're going to get into that in a bit. All right, so what is a probability distribution? The distribution of probabilities for selecting each category or value of a variable. So the book gives the example of flipping a coin. The probability distribution of the possibilities of getting heads is 50% and tails is 50%, right? So in a bit more complicated way, we do the same thing in social research. We construct the probability distribution for a single variable. So sampling error is something we'll talk about a lot in this lecture. So when there's a difference between the sample estimate and the population value that's actually being estimated. So in research, we don't know the sampling error or how far off our estimate is because we don't know the distribution of the population. That's kind of why we're drawing a sample in the first place. So we need a way to know how much sample estimates are likely to vary and how confident we can be in a single estimate based on a sample of a given size. So to do this, we get the information from a sampling distribution. So what the hell is that? A sampling distribution is just a probability distribution of a sample statistic, or like a mean or proportion, for all possible samples of a given size. So really, it's a theoretical distribution of sample results for all possible samples of a given size. It can tell us the probability of obtaining our estimates. So when we look at the characteristics of the sampling distribution of a mean or proportion, really you just have the mean of all sample estimates equals the population mean, right? You want them to match up so that what you're seeing in your sample reflects the overall population. Another important point is that the standard error decreases as the sample size increases. So this is why we want to have larger sample sizes so that we can control the standard error. And also there's this assumption that it's going to have the shape of a normal curve, which I'll show you a picture of in a second so you know what I'm talking about. Okay, so in this, this is a sampling distribution that shows the probability distribution of a sample statistic. So in most cases, this is a percentage for all possible samples. In this table, it shows the number of possible samples of a size of 500, each drawn randomly from a population of 50,000. So technically, a population can be infinitely large, right? So when we say it's theoretical, that just means it comes from probability sampling theory, the actual, the way that they calculate these ideas of what these estimates are. So this one is actually related to the example from your book, right? Because remember, the most fundamental principle to this whole thing is that your standard error decreases as the sample size increases. So this figure here just kind of illustrates that. So you see that there's more clustering in the same area, there's less variation when you get a larger sample sizes. All right, and then this is that bell curve, right? So all of these fun statistical measures of sampling distributions assume a normal distribution. It's also called the normal curve or the bell curve because, hint, it looks like a bell, supposedly to people. So it assumes that if the variables are not related, then scores are going to be evenly distributed across the variable. So in a sampling distribution, predictable percentages of sample estimates fall within measurable distances of the population value we're estimating. Hence, you have between the first standard deviations, 68%, between the first two, or between two, you get 95% or 99%. Later, we'll talk about how 95% and 99% are really what we call our confidence intervals. Okay, so statistical inference. Knowing the sampling distribution, we can determine how confident we are that a population's value lies within some range of a sample estimate. So levels of confidence are just how many standard errors we add and subtract from the sample estimate, like in the bell curve model from the previous slide, right? So researchers make interval estimates of population characteristics. Rather than using single point estimates, statisticians construct interval estimates. And interval estimates themselves are based on three values: the best single estimate, or the mean, the standard error, which again is based on the sample size that you have, and the level of confidence, which again usually is 95 or 99%. And confidence intervals, this is how they're calculated, because I know you're like, hey, I want to do the mathematical calculations by hand at home. Here's that relationship, right? How this is calculated. The confidence interval for the mean, it just equals the sample mean plus and minus the confidence level times the standard error. So remember, a confidence interval is just a range within which a population value is estimated to lie at a specific level of confidence. So it's like saying, if you're at a 95% confidence interval, you're saying that you're 95% confident that the actual population values fall between those ranges you've suggested. So in the sample one in the book, on the slide a couple back, it was 40.6 and 49.4. So 95% confident respondents will fall within that range. Okay, so the next step in your process of probability sampling is defining the target population, or the people that you're trying to study. And then you need to construct a sampling frame, which is your basis for how you're going to sample, devise a sampling design, determine the size of your sample, and then the fun part, actually draw that sample and collect some data. So we're going to go through each of these in detail in the next few slides here. All right, so first, your target population. What is your target population? It's just the population to which you're trying to generalize your sample results. So this needs to be spelled out in detail. So it's similar to a conceptual definition and measurement. You need to specify which cases are included and which are excluded based on your unit of analysis that you're using, based on your research topic, based on the specific considerations of your methodology, right? So this is why it's a bit tricky, as it should be what fits your research question's aim. So it's not exactly the same in each research situation. And remember, part of being so specific is so that you can later measure the data in a way that's specific enough to measure what it thinks it's measuring, and to be something that other researchers can look at to determine its validity, as well as give others the opportunity to replicate the research to make sure it's peer-reviewed, right? And can add to the knowledge that we have about a particular topic within a paradigm. So, how do you sample the target population? Well, you have to construct a sampling frame. So a sampling frame is just a list or rule that provides the basis for sampling, where you basically find a way to identify the people in your population. So similar to an operational definition and measurement, so you already conceptualize what this group would be. Now you're operationalizing how these things will be measured. So in this figure 6.6 from your book, this is trying to illustrate the importance of your sampling frame connecting to your target population correctly, so that your sample is an accurate slice of that overall population, which then gives you the opportunity to extrapolate your findings onto the larger population you're studying. So if your sampling frame is imperfect, then your sample may not be an accurate representation or slice of that total population you're studying, which again means that your findings would not necessarily be something you could extrapolate to the general population, which is kind of the whole point of using probability sampling. Okay, so different kinds of these designs. The thing that makes probability samples the same is that each case has a known non-zero probability of being selected, but they do differ in some ways, as for some types of probability samples, the chance of being selected is not equal, though it is for others. So we're going to get into the different kinds a bit in more depth. First, you have simple random sampling, which is the sampling design where every combination of cases has an equal chance of being selected. So this is, again, that simple put everyone's name in a hat probability, so there's an equal chance of selection. This usually requires a complete list of the population so that you can draw any potential person that fits your requirements. So this is easy to do with a sample as small as this class, right, to put all the names in a hat. But obviously, if you're trying to pull large samples from a large target population, you'd need a pretty big hat, right? Or in this case, a list of the population that you could draw from. So if you wanted to study as your target population Cal State Fullerton students, you'd need a list from admissions. So you could use, that to send a survey to the people that you'd pick as your sample or slice from that overall list. But their likelihood of receiving the survey would be equal, right, in that scenario. The next kind is stratified random sampling. So this is an independent, simple random samples that are drawn within different stratum or variable categories. So the stratum example in the book is using age ranges as strata or subpopulations that you divide your sampling frame into. So there's reasons why you would use this instead of just the simple random kind. It's used to sample small subpopulations and also to reduce sampling error. It's optimally efficient when stratifying variables are related to an estimated population characteristic. So that just means that stratified sampling increases your efficiency by reducing the standard error of the sample so that the estimates are more precise in regards to the population's characteristics. So that's a plus, right? And they're controlling for variability, which, remember, the more variability, the higher standard error. So by controlling variability, you're lowering the standard error. The only loss of efficiency is when you compare it to simple random sampling, because to do a stratified sample, you need to divide the sampling frame into the strata and draw those separate samples. Clearly, it's more efficient to do it once and not a bunch of smaller ones, but that's why the book refers to it as optimally efficient, right? Also, you want your sample population's proportions to meet those of the larger population. So if 45% of respondents are male when studying calcifullerton students, you have to make sure that reflects the population of men on campus at 45% of the overall population. So strata, again, may be sampled proportionate or disproportionate to the population's composition. So you do want to make sure it's proportionate. So to do this, researchers have to make statistical adjustments to their sample characteristics to make sure they're a little more accurate, right? More accurate reflections of the overall population. So they call it weighting, like weighting a variable, which is correcting for the unequal probability of a strata compared to the overall population. And then the last kind of probability sampling design is cluster sampling. So the previous two types assume that you have some sort of list of the total population that you're trying to study, but what if you don't, right? Or what if it's impractical to have such a list? So in these cases, cluster sampling is used. And in cluster sampling, the population is broken down into clusters, or really just small groups of cases. So they are almost always multi-stage, which means that samples or independent samples are drawn from each cluster or natural grouping. And these natural groupings that they give examples of what that means in the book, but like a university could be considered a cluster if you selected it from the overall CSU system as a cluster of the overall population you're studying. In this case, CSU students statewide, right? So again, cluster sampling is mostly used to reduce costs of compiling a list or reaching widely scattered respondents. And while they save on money, they're less precise than either simple random samples or stratified random samples. So usually to counter this weakness, there are more clusters selected in a multi-stage way. And they use probability proportionate to size sampling. So that means they can stratify clusters just as we stratified individual units in the strata example in stratified random sampling. So one problem with clusters is that natural clusters often vary considerably with the cases they contain. So continuing with that CSU example, some campuses are larger in student populations than others. Some are different in gender or racial or ethnic variation than others. So in order to make this not a problem, clusters can be stratified, but population size, which again means the sample better represents the overall population, they call this kind of probability proportionate to size sampling. So again, going back to weighting variables to make sure that the proportion of the sample that you're using reflects the overall population. And then over here, this figure on the slide is an example of a two-stage cluster. So they pick a chunk of their primary area and sample location and a segment of that location, which breaks down to an individual unit of analysis, or in this case, a specific housing unit. All right, so next step, determining sample size. So what are the two main considerations in determining an appropriate sample size? Well, the first would be desired precision or margin of error. So precision is very important when it comes to research methods. Just like in life, no one likes waiting for the cable guy when he says he'll be there between 9 a.m. and 2 p.m. But if they said they'd be there between 9 a.m. and 9:30 a.m., you can better plan your life around that interruption. Obviously, in this case, we're talking about convenience that precision gives researchers, right? Not just having to wait around your house for some guy to show up. But really, when you narrow the focus, you can make sure that you reduce error and that you're measuring what you think you're measuring precisely. So the absolute size of the sample is what determines the precision. And the sample doesn't need to be enormous to yield very precise results. So sampling error tends to be quite small for samples of about 2,000 to 3,000. So increasing a sample size higher than that is really not going to decrease the error that much. So it's really not worth the additional cost to have a larger sample than that, because available resources is another big consideration you have to make when doing research. Money and time have to be considered because research isn't free. Getting someone to finance it, you need to justify these increased expenses. So if sampling 3,000 people nets pretty much the same error as sampling 10,000 people, then how are you going to justify that you need to sample 10,000 people when 3,000 would do, right? Okay, so there are these issues of sampling error, which we talked a little bit about before. There's different kinds of error that can occur in probability sampling. The first is just random sampling error, and this is due to random selection. So we talked about how, you need to reduce sampling error to make sure your sample estimate is true to the population value. So as I mentioned before, you can estimate the error and reduce it by increasing the efficiency or the size of your sample. But there's also two different kinds that we haven't talked about yet: coverage error and non-response error. So coverage error is just due to mismatch between the target population and the sampling frame. So it was in that figure that showed how the sampling frame needs to encompass the overall population you're studying. So if your sample or slice of that population is coming out of a coverage error, you're not actually studying what will reflect the overall population. So your findings don't extrapolate to the larger population, which is kind of the whole point of doing probability statistics. So yeah, you want to make sure that there's not coverage errors. Going back, non-response error as well, due to incomplete data collection. So this is really when maybe those people who were sampled individuals did not respond. Like, let's say you administer a survey to Cal State Fullerton students and you send out a representative 100 surveys and 20 people don't respond. Maybe they somehow differ systematically from those who did respond. So maybe those students who are really dedicated would not respond because they don't want to take too much time away from their studies to participate. Or maybe the ones who didn't respond vary in some significant way from the sample that did respond. So again, this is called non-response error or non-response bias. So then there are times when you should use non-probability sampling or non-random methods of case selection. So when is this typically done? Well, first, for practical reasons. So this is done when only a subset of the population is accessible. So if they're rare, like if you wanted to study transgendered individuals, or the example of the book was Vietnam War vets, right? It could be difficult to construct an adequate sampling frame for something like that. Also, if it's not possible to obtain it or construct an adequate sampling frame, it makes sense to pick a sample with non-probability sampling. So especially if the target population is unknown or hidden. So let's say you wanted to study drug users. It's not like you can just pop over to the government list of drug users and randomly select people from that population, right? The population's unknown. Or let's say, in the same case, a list of the homeless or the undocumented, right? You get where I'm going with this. When you don't know the extent of the population, or if the population is hidden, it makes sense to pick a sample with non-probability. Also, it makes sense when the aim is to develop a holistic understanding of a group. So if you're studying a field site and you as the researcher pick individuals you meet to include in your research, this makes sense if you're trying to understand a group and you feel that these people are best suited to help you do that. So this is where the researcher makes these kind of expert judgments about who fits the scope of their sample to reflect the population that's being studied. So choosing someone at random does not really make sense in these situations. And also, when the cases are selected to advance theoretical understanding. So again, the researcher will find those with the information and insight needed to be helpful to illuminating their theoretical understandings. Like if I was going to interview the homeless that live on the side of the 91 freeway encampment, I'd probably select people who were, number one, willing to talk to me, right? Number two, did not face debilitating mental health issues, right? Maybe I would interview people with variable ages so I could see how homeless youth, their experiences differ from those seasoned adults that have been on the street for years. So I would carefully select individuals, keeping in mind that I do not want to only interview a select group that may skew this, like only homeless youth, right? And then try and apply my findings to all homeless people. I would need to make sure I'm still sampling to my population that I'm trying to study. So the steps that they talk about here in non-probability sampling is just that you need to select cases or sites and then select observations, which we're going to go through right now. So first, selecting cases or sites. What factors guide the selection of one or a few cases? Well, the first is that they're convenient and accessible, right? They're located somewhere close to the researcher or they're accessible to the researcher. Next, they have to fit the research topic, so they can help explain what the researcher is looking to explain. So if you wanted to study interactions between professors and college students, your site choice would logically be a college or a university, right? Also, how you select cases or sites should provide relevant theoretical comparisons, right? You're looking at previous data to set up your understandings of your hypothesis in your literature review. You already know what theoretical understandings are there from previous research. You could then, try to parallel these things. And also, when you're looking at extreme or deviant cases, then, you really need to have these kind of very clear ways to pick cases that actually fit that criteria, right? People that are extreme or very deviant are not the norm. So therefore, doing a probability like sampling would really not make sense because you wouldn't get those outliers. All right, and then as far as selecting observations, the first step again is selecting the site itself, but then you have to pick the people you're going to study or observe in that particular site. So how are the people in the observations selected randomly or non-randomly? Non-randomly. The first way is convenience sampling. So most appropriately, this is done in early stages of research when you're picking a number of people that are convenient and accessible to you. So for this class, you'll probably use this kind of sampling to get people to take your survey. So people in your class, people in other classes you're in, people in your social media landscape, etc. As it's not necessary for you to get a complete list of all possible people, you just need to get some responses and get it done. So this is, the typical means of selecting in a lot of experiments. There's also purposive sampling, which applies to both research sites as well as other units of observation. So again, this depends on the knowledge and judgment of the researcher who is going to have insight and knowledge about this particular group or unit of analysis they're studying from their previous research that they've done in their lit review. That's going to give them an idea of who would be an appropriate sample or not. So this is going to provide broadly representative samples, more so than exactly representative through the probability sampling. And lastly is snowball sampling. So this just follows a process of chain referral. So you find people that fit your scope, and then you can ask them for any other people that may be interested in participating. So I've done this approach before in my own research on political party affiliation. When my initial respondents that were registered Republicans fell through, I used snowball sampling, or just contacts from people I'd already interviewed, to find more respondents that fit the parameters of my research. So this is very useful in locating small and deviant subpopulations. So let's say, again, you're studying drug users, right? And since there's not a list or a super specific location to find all these users, contacts who would be willing to participate from, like let's say you interview someone that's applicable and you ask them if they have anyone they know that would be willing to participate, it's a good way to get more applicable respondents that fit the frame of what you're trying to measure within your research.